Good afternoon, good morning, depending on where you are. We are continuing with our lectures in thermodynamics. So let us look at distillation of liquids. And our focus today will be steam distillation. Now we have certain chemicals which are very soft, especially organic chemicals. And remember, organic chemicals contain carbon, and you might not be able to distill them or separate them at high temperatures. So you need complementarity in terms of vapor pressures to help assist you reach the atmospheric pressure. So that if, for example, you take two mixtures, A and B, which are completely immiscible, they're immiscible. In other words, they don't mix. It's not like miscible liquids, which when you mix like ethanol and water, they form a homogeneous solution. No, they are immiscible. In other words, they will be separated into different phases. For example, if we say we have immiscible liquids, A and B, you can think of that as having this mixture of A and B in a container. Let's say you have a container there, you have the mixture A and B, and they are so separated that there is like a boundary between them, so that there is A on this end and B on this end. And so that the total pressure here on top here, let's call that total pressure P, is the same as the individual pressures of those pure components. That is, the total pressure P, which we call P, can be expressed as P is equals to the pressure of the pure vapor pressure of pure A plus the vapor pressure of pure B. Very important for us to note that. Therefore, in terms of the mole fraction in the vapor, if you go back to our derivations involving the lever principle in one of the lectures, then you will see that we talked of the mole fraction in the vapor and the mole fraction in the liquid, and they're denoted as Y for the vapor, X for the liquid. So the mole fraction of A, that's the mole fraction of A in the vapor is given by its vapor pressure divided by the total pressure. Similarly, the mole fraction of this other component B, YB, will be given by the vapor pressure of B, pure component, over the total pressure. So that the ratio of the mole fractions YA over YB will simply be PA naught. This is PA naught. Let's denote them. PA naught is the vapor pressure of pure A, and PB naught is of course the vapor pressure of pure B. So that if we take the ratios of those two pressures, then we are going to have PA naught over P divided by PB naught over P. That will be simply PA naught over PB naught. Now, remember, when we're talking of moles of material, then we are talking of the number of moles of A is mass of A divided by the molecular weight of A. That is molecular weight of A. Similarly, for B will be mass of B over molecular weight of B. So if we bring that into the equation there, so that we simplify our work, if we bring that expression there in the equation, we will have now YA over over YB is the same as mass of A over its molecular weight of A divided by mass of B over molecular weight of B. And this is equals to P A naught over P B naught. So that if we rearrange that fraction there, remember MA, we are saying is mass of A, MB, mass of B, and MW, M capital M, A, molecular weight of A, and B, molecular weight of B. So we can now proceed and simplify these expressions there. We can simplify those expressions there so that we get some information which can help us in that process of distilling those two immiscible liquids. So if we reorganize this, then we see that when we reorganize this expression, then we see that MA, capital MA, MB over small mb is equals to PA naught over PB naught. And so if we rearrange this to find out the masses of the components in the distillate, we will have MA over MB, MA over MB is equals to PA naught, molecular weight of A, molecular weight of B, over PB naught, molecular weight PB naught. Now this molecular weight of A and PB naught, we have that going that side, A, that's going to B, PB naught, molecular weight of B. So we are seeing that we have gotten the mole fractions. A mole fraction of A is mass of A divided by its molecular weight. Mole fraction of B is mass of B divided by the molecular weight of B. So this is simplified, like we have said, to MA divided by MB divided by MB. Okay, MA divided by MB, and then we have that quantity there, that because that is that's MA divided by MB, and that is we have MB divided by MA. We have missed out something there. We have MA divided by MB, so that's there, MA, MB. Then we have the molecular weight of A and molecular weight of B. Very good. So we are okay. So what does that mean? It means that the ratio of the masses of components A and B in the distillate is related to the vapor pressure of the pure component A times the molecular weight of A, and vapor pressure of pure component B times the molecular weight of B. So with the ratio of the masses on distillation is dependent on the vapor pressure of the pure components and their molecular weights. Very important for you to note that when you're dealing with soft chemicals, organic chemicals, these are chemicals which, if you heat them excessively, they degrade. So what you do is sometimes you can mix that organic chemical with water. And so what you have, we have said the total pressure basically will be the sum of the vapor pressures of the individual components. So that one will allow this liquid to boil at relatively low pressures, because remember, boiling is when you balance the two pressures. So now you'll have an assistance think of it that way. You have an assistance, for example, from the water. So you will quickly reach that pressure, that atmospheric pressure, which you have to balance so that the thing boils. So it will boil at a lower pressure. The mixture boils at a lower pressure than that of the individual components. Therefore, the mixture will boil at a lower pressure. A lower temperature than in the case of individual components. So that if the balancing pressure was PA and you have the individual component P1, they need to balance. So when you add the second component P2, now you see you will quickly reach this particular pressure faster than that, because if P1 is equal to PA, now when you add the other one, now this one will be much greater than PA, so that will be relatively significant, so that you quickly reach PA. So that complementarity assistance is very, very important. That's the importance of steam distillation, so that you're able to distill those very sensitive or soft chemicals which can degrade, for example, when you expose them to excess heat, but at the same time you want to distill it. So you can make use an immiscible component, and then you will find that now you can boil it. It will boil at reasonably lower pressure than if it was individual. So you avoid the degradation or the denaturalization of that particular chemical. So let's stop at that. We'll continue with the lectures later.